have just learned the mathematical model of quantum information. We know that quantum information is represented by qubits, which are vectors in two-dimensional Hilbert space. And for a system with multiple qubits, for example, with n qubits, the vector will be in a space with dimensionality 2 in the power n. But for computations, we need more. We need not just to store these qubits, we need also to modify them. So we need to modify these vectors in Hilbert space. And the physicists will tell us that any such modification must be unitary. So any computations, any program for a quantum computer must be represented by a unitary operator. Let's recall this notion, a unitary operator. It is a linear operator for which its adjoint operator is also its inverse. And the matrix of an adjoint operator is the conjugate transpose of the matrix of original operator. So this is our definition of unitary operator, and these unitary operators also have a very important feature. They preserve the length of the vectors, so the norm of ux will be equal to norm of x, and they also preserve the inner product, so they preserve angles. So if we have x u y, and it is just x and y. And this, among with linearity, is the sufficient. It is sufficient for an operator to be unitary. So if we have some square matrix and we have to check if it implements some unitary operator, we can either check this, or we can check if this operator maps an orthonormal basis to orthonormal basis. Let's see some examples. The Hadamard transform, already a familiar name to us. So this is the matrix for the Hadamard transform, probably the most used operator in quantum computations. And H star here is itself, because we don't have imaginary parts here, so we don't have to conjugate, and the transpose is also changing places of these ones. Let's multiply h by h. So it's 1/2, 1 minus 1. One multiplied by 1 plus 1 multiplied by 1. We have 2 here. And 1 multiplied by 1 minus 1 multiplied by 1, 0. And again 0, 2. So it is just a matrix of identity operator. So, okay, we can see that H is unitary. Let's see how it acts on our bases 0 and 1. So H0 is square root of 2, 1, 1, 1, minus 1, 1, 0, which is 1 divided by square root of 2, 1, and 1, which is just this vector, the mark plus. And maybe not a surprise to you that when H acts on vector 1, it gives us Adamar minus. So the Adamar operator, the Adamar gate, maps our traditional normal basis 0, 1 to the Adamar basis plus minus. And of course, since H is its own inverse, H of plus equals to 0 and H of minus equals to 1. Another very useful operator, which we call X, the matrix you can see on the slide. Let's see how it acts on our basis 1, 0. So X 0 is 0, 1, 1, 0, 1, 0, and we have 0 here and 1 here. It is 1. And X of 1 is again 1, 0, 1, 1, 0, 0, 1, and we have 1, 0, 0. So it maps our standard basis 0, 1 to itself, but it flips it. So it is actually the quantum implementation of NOT operator. And since it maps orthonormal basis to orthonormal basis, we can be sure that it is unitary. The next operator is C0. All the previous operators were matrices 2 by 2, so they acted on the spaces with 1 qubit. This operator acts on a space with 2 qubits, since it is a matrix 4 by 4. Let's see how it acts on our standard 4-dimensional basis. So C0 of 0, 0, it's this matrix on this vector. And it's actually itself. So it is again 0, 0. With 0, 1, we will have the same result. It's mapped to 0, 1. And you can easily check that 1, 0 will be mapped to 1, 1 by C0, and 1, 1 will be mapped to 1, 0. So again, this operator maps orthonormal basis to orthonormal basis, thus it is unitary. And we can see that it flips the second qubit only if the first qubit is 1. So it is a conditional NOT operator. This bit, the highest bit, is the control bit, and this bit is under the control of the controlled bit.